If you look at the skeleton of a skyscraper or the frame of a bridge, you rarely see solid blocks of metal. Instead, you see hollow tubes and I-beams. This isn't an aesthetic choice, it's a direct response to the way physics handles internal stress. When a solid beam bends, the internal forces are distributed unevenly. The material at the very top edge compresses, and the material at the bottom stretches. As you move toward the middle of the beam, those forces decrease linearly, leaving a neutral axis right across the center where the stress is exactly zero. Because the material near that neutral axis is doing almost no work, engineers remove it to save weight. By carving out that center and shifting the mass to the extreme edges to create an I-beam, we place the material exactly where the bending forces are highest. This document illustrates the mathematical logic of the I-section. Efficiency is achieved by maximizing a property called the moment of inertia, or I. By distributing the area as far from the neutral axis as possible, an I-section carries a significantly larger bending moment than a solid rectangle of the exact same weight. Many structural components are not perfectly symmetrical. This T-beam, for instance, features a heavy top flange and a narrow vertical web. Unlike an I-beam, its cross-section is visually and mechanically unbalanced. To maintain physical equilibrium in this shape, the global neutral axis cannot stay in the geometric center. It shifts upward, anchoring itself closer to the center of mass of that heavy top flange. Calculating the total moment of inertia for this composite shape requires the parallel axis theorem. We split the T-beam into two simple rectangles, find the local stiffness of each, and then measure the exact distance, denoted as d, from each segment's local center to the global neutral axis. The theorem directs us to add the area of each segment multiplied by that distance squared. Because the distance is squared, the math rewards material placed far from the bending center and penalizes material trapped near the neutral axis. Finding the total moment of inertia for any complex beam is simply a summation of the local stiffness of its parts plus the geometric advantage gained by their distance from the center. Now consider this T-beam functioning as a cantilever. It is anchored solidly to a wall on the right and supports a uniform downward load across its entire length. Based on this physical setup, where along the beam is the bending moment highest, and which edge is currently in compression? Because the wall must resist the leverage of the entire beam's weight, the bending moment peaks right at the fixed support. As the beam sags, the top flange is pulled in tension, and the bottom edge is pushed into compression. This hand-drawn diagram illustrates the consequence of our shifted neutral axis. The distance to the extreme top fiber is a short 35 millimeters, while the distance down to the extreme bottom fiber is nearly double that, at 65 millimeters. Because stress scales directly with distance, the compressive stress at that bottom fiber is significantly higher than the tensile stress at the top. The bottom edge is under much more mechanical strain simply because it sits further from the neutral axis. When designing with asymmetric beams, you must check both extremes. Structural failure will always initiate at the fiber located furthest from the neutral axis. The Flexural formula, where stress equals m times y divided by I, allows us to calculate the exact stress acting on any internal layer. It proves that normal stress varies perfectly linearly with the distance y from the center. This establishes our first pillar of design. Economic sections push material to the extremes to maximize strength and minimize unnecessary weight. Second, the parallel axis theorem quantifies the exact structural advantage of moving that material away from the center. And third, the Flexural formula acts as the absolute mathematical link between the shape of a beam, the applied moment, and the resulting normal stress. While these normal stresses explain how a beam resists bending, they also create a secondary force where the horizontal layers of the beam attempt to slide against one another. This introduces a separate structural threat, longitudinal shear, which we will investigate in the next lesson.